Hi everyone, I'm Shanmukh Sanan, and this is the presentation which is part of Artificial Intelligence Foundations and Applications term project. And in this presentation, we'll be talking about the topic AI in object detection. So we are a team of 4 members, and we'll be presenting the contents that are being present in this table corresponding to each of us. Firstly, I will introduce the problem statement, what is object detection, and what are the applications, challenges, and how are each of the methods classified. Later, Jitendra will be introducing a few of the famous deep learning approaches for this task. And Pratik, Jitendra, and Aryan, each of them will be explaining one paper each, which are being released recently in this field. Finally, we'll show how each of the existing approaches perform on a publicly available data set. And we'll give at the end we'll give summary of the presentation. What the future approaches and what are the challenges that are being faced currently. Coming to introduction, so object detection. It is part of a computer vision field where we'll detect, classify, and draw a bounding box around images, semantic objects of an image or any video. So it has wide range of applications like self-driving cars, face detection, anomaly detection, and video surveillance. This is a very challenging task, considering the complexity of image or a given video, which will have many features, and also the problem that is being given, that is predict drawing bounding box around each object that is being present in image. Uh, it is very difficult to solve such a task in traditional approaches. Even the results show the same thing, which we'll discuss at the end. So there has been a lot of research in solving this task using AI approach. Coming to general challenges, first is intra-class variation. Say for a given image, you can have many number of changes in that image. Like we can change the brightness, contrast, occlusion, the pose of that person or any object, and even view. There can be different point of views for a given image, which will make very difficult for a given algorithm to detect. And even say a traffic image or a given video surveillance task, they can have number of faces or classes to be detected and classified. It requires high quality and annotated data as well as very large and accurate models. And coming to efficiency, say current day models are very uh, current day models require high computation resources to process image as well as perform the detection task. And considering that computation need, it will be very difficult to deploy them in mobile or edge devices. So efficiency becomes a bigger problem in this field. So these are some failures with traditional methods. Traditional methods of object detection or any generic image recognition task, they build handcrafted features or rule-based features, which are then being used to detect and classify images. So these handcrafted features will not work if there is any small change in the image scale. Say if you input 256 cross 256, and we have performed the task. And if you change it input dimension to 512, then the model this uh, approach will not work. Even small change in occlusion or any uh, brightness or contrast will make it a failure. Even high computation expenses are there for this task, and large annotation data set is required, which is very difficult to get for this object detection. This object detection issue is divided into three parts. First one is one-stage detection, two-stage detection, and transformer-based model. So these stages are decided by these two questions. One is whether there is any object in an image, which is kind of image classification task. And second one is if yes, what objects and where. So this what says that it is a classification, and this where is nothing but drawing a bounding box around object, which means a regression task. So this object detection is mix of classification and regression data. So the transformer-based models is nothing but an one-state detection, but this is being written as separate uh, type, considering the model structure as well as its recent success. So coming to one-stage detector, one-stage detector predicts bounding box over images without any regional proposal step. It will make it faster when compared to two-stage detectors. So a single feature extractor network will be present, which will extract feature maps from the input image, and these feature maps are then being sent to two branches. One branch will first branch will be classifying the classes of the object, and second branch will be drawing bounding boxes around them. A two-stage detector has a new network known as regional proportional network, where it will propose a set of regions. Regions are nothing but cropped part of a given image, and these proposed regions are then sent to uh, the two branches that are being discussed before. Transformer-based models. So these transformers are firstly introduced in field of NLP. They have a very large impact in the natural language processing field. And the high level is that they have an attention-based model where they will establish dependencies among the elements of sequences, and they can attend to longer context, which a generic LSTM or CNN or RNN cannot do. So this success has shown its interest in computer vision applications. So firstly, this transformer is used in image classification tasks. They have shown state-of-the-art results when compared to the performance of efficient net or ResNet in image classification. Been work that that is being done to use these transformers in object detection and segmentation tasks also. So the main idea is that when we go to one state detector, we have a feature extractor layer which can be replaced with a generic transformer encoder decoder network to generate feature maps from a given image. And later the steps remain same. And next, Jitendra will be explaining or show the papers or the work that is being done so far in this field using AI approaches. Thank you.
Yeah, thank you, Shanmugh. I am Jitendra and I will take the discussion forward. As we know that object detection has three categories, namely one-stage detection, two-stage detection, and transformer-based. The examples of one-stage detection are efficient det, series of YOLO algorithms, and SST. The examples of two-stage detection are RCNN, fast RCNN, faster RCNN, and mask RCNN. And the examples of transformer-based are DETR, Swin Transformer version 2, and VIT. Now let's take a look at the evolution of object detection. RCNN was introduced in 2013, followed by YOLO, faster RCNN, and SST in the year 2015. Correspondingly, YOLO 9000 was introduced in 2016, RetinaNet and masked RCNN in 2017, YOLO version 3 in 2018, Efficient Det in 2019, YOLO version 4 in 2020. The research on load vision transformers commenced in 2020. RCNN, fast RCNN, and faster RCNN are series of two-stage detectors, which focused on improving the previous one. YOLO is the most famous and largely used object detection model. From its introduction, there has been a lot of work in improving the model performance and speed. YOLO X and Swin Transformer version 2 was introduced in 2021 and Vision Transformer YOLO version 5, version 6 and version 7 in the year 2022. Now, I will walk you through the survey papers in detail. There are three most recent and important research works in the field of object detection. They are efficient det, YOLO series, and DETR. These methods gave us desired results on many existing object detection datasets. Coming to efficient det, two contributions were made in efficient det: bidirectional FPN and compound scaling. Bidirectional FPN allows bidirectional fast multi-scale feature fusion. The primary goal is to accurately aggregate multi-scale features in a top-down manner. Compound scaling. It scales up backbone, feature network, box or class network, and resolution. With the help of bidirectional FPN and new compound scaling, a family of efficient data networks are formed, which turn out better in performance than older object detectors in terms of accuracy and efficiency. Typical FPN. As you can see in figure A, it fuses multi-scale features from level 3 to level 7. As you can see in following figure, the the PANet architecture adds an additional bottom-up pathway on top of FPN to make use of the lower level features efficiently. The relationship between the nodes can also be found by using a neural architecture search, NASFPN. Efficient det initially removes the nodes that only have one input edge and creates the simplified version of the PANet. After that, an additional edge from the original input to the output node is added if the nodes are at the similar level. A bidirectional top-down and bottom-up path is treated as a single feature network layer, and it repeats the same layer multiple times to enable a higher level feature fusion. The goal of compound scaling of the network is to amplify up a baseline model, efficient at D0, to cover a wide spectrum of resource constraints. A simple compound coefficient psi jointly amplifies all dimensions of the backbone network by directional FPN. A heuristic-based scaling model is implemented because object detectors have much more scaling dimensions than image classification models. Thank you. Now I would like to hand over the presentation to Mr. Pratik VNS.
I'm Pratik. I'm going to speak and present about YOLO series. YOLO series, frame object detection as a regression problem to spatially separated bounding boxes and associated class probabilities using a single neural network. There are three main fundamental parts of YOLO. One is residual box, bounding box regression, and the other is intersection over union. A residual box. Model divides the incoming image into grids of equal dimension, where each grid is responsible for detecting an object or a part of the object that appears inside the grid. Bounding box regression, objects in each cell are highlighted with a bounding box that has attributes such as weight, height, class, and center, etc. YOLO predicts these with a bounding box regression representing the probability of an object appearing in the bounding box. Intersection over union, IOU. IOU describes the overlap of bounding boxes. Each grid cell is responsible for predicting the bounding boxes and their confidence scores. The IOU is calculated by dividing the area of the overlap by the area of union. The IOU is equals to 1 if the predicted bounding box is same as the ground truth bounding box. This way, it becomes easier to eliminate the bounding boxes that are too different from the real box. Each grid cell of an image predicts the bounding boxes with particular probability scores as well as class probabilities for each object. The IOU ensures that the predictions are in line with the ground truth, um, so that the final detection ends up in unique bounding boxes that enclose objects perfectly. The given picture is of um, represents the YOLO architecture, and versions and variations of YOLO. There are quite a few different versions of YOLO. Few of them are YOLO, YOLO 9000, YOLO V3, YOLO V4, YOLO V5, so until YOLO V7 and YOLO X. The improvements and the features. YOLO improved detection time and accuracy over existing approaches. YOLO 9000, it has a significant improvements on anchor boxes and higher resolution and has the ability to detect over 9000 class objects. YOLO V3 had an additional objectivity objectivity score to the bounding box prediction and connections to the backbone network layers. It also provided an improved performance on tiny objects because of the ability to run predictions at three different levels of granularity. YOLO V4 introduced the novel improvements, including mind activation, improved feature aggregation, etc. YOLO V5 is 90% smaller than the YOLO V4 um, version and faster inference. YOLO V6 iterates on YOLO backbone and neck by redesigning them with the hardware in mind. Introduced efficient rep backbone and rep panic, anchor free training, and SIOU box regression loss. YOLO V7 model reparameterization, compound scaling, and the architecture ELAN extended efficient layer aggregation networks, which changes the computational block. YOLO X switched YOLO detector to an anchor-free manner and implemented other techniques like decoupled head, leading label assignment strategy, etc. This is about YOLO series, and my other mate will be continuing with DETR. Thank you.
Hello, my name is Aryan and I'm going to be discussing about the DETR one. So DETR is basically detection transformer. Detection transformer streamlines the detection pipeline and removes the need of hand-designed components like a non-maximum suppression procedure and anchor generation, which explicitly encode our prior knowledge about the task. DETR proposes a set-based global loss that forces unique detection via type rate matching, which also uses a transformer encoder decoder architecture. Given below is a DETR architecture, which consists of backbone, encoder, decoder, and prediction heads. So I'm going to be discussing about the steps on which the DETR actually works. So DETR is the conventional CNN backbone to learn a 2D representation of an object image. Typically, the output has channel number C2048 and H equals H mod by 32 and W equals mod by 32. The model flattens it and supplements it with the positional encoding before passing it into the transformer encoding. Then, the transformer decodes the input into a small fixed number of learned positional embeddings called object queries and additionally attends it to the encoder output. Each output encoding of the decoder is passed to a shared network FNN that predicts either detection or a no object class, that is the normalized central coordinates height and width of the box with respect to the image input image and the class labeled using softmax function. Auxiliary losses are added in decoder using training, especially to help the model output the correct number of objects of each class. Prediction FFNS and Hungarian losses are also added after each encoder layer. Next, we are going to be discussing about the performance of each of the models and also their average precision in measuring that. So, given here is the average precision to models ratio. So, as we discussed earlier, we discussed about efficient YOLO series and also DETR. So, box AP generally represents the average precision. So, AP is a popular metric in measuring the accuracy of object detectors like faster RCNN, SSTs, and then YOLO 9000, etc. As you can see, the average of the DETR model is the highest. So basically, so generally DETR model is used for the object detection. So we're going to moving on to the summary part. So as discussed earlier, we discussed about various detection methods and their models. So single state detection method works well when compared to two stage detectors. Also, vision transform models do perform well when compared to other models. Vision transformer requires large data to start training from scratch. Untraining data in that scale is difficult for object detection tasks. There were a few works which tried resemble of one stage and two stage detectors, which is YOLO and RCN, which gave improvements in results. Below down are also given some of the aspects in which the object detection can be improved or implemented. So training can be done with less data from scratch, which requires less processing and less time taking. Also, use of automatic neural network and or architecture search like NAS for determining the hyperparameters of detectors can be used as well. Designing more accurate and lightweight models for the prediction part. So using the same model trained on one data in the other, which has relatively less data, can also be done. Ability to train on weakly supervised data, that is, image level labeled data, could result in considerable reduction in the costs for the. And so that is all about the object detection, and that's end of the session. Thank you.